We're going to go back to finding limits, and we're going to talk about something called the Indeterminate Form and L'Hopital's rule. L'Hopital's rule is actually written by the Bernoulli brothers. L'Hopital was a French aristocrat who did a little bit of mathematics, and he wanted to have his name on a rule, and so he paid the Bernoulli brothers to develop one for him. So really, it should be called the Bernoulli rule, but L'Hopital's name has been stuck ever since. So I guess he did get what he wanted. And L'Hopital's rule is to help us find limits. So if I want to find, let's say, a function f of x equals x squared minus 4 over 3x squared minus 2x minus 8. Let's say this is my function. If I want to find the limit as x goes to 2 of this function, well, if I put 2 in the top, I'll get 0. And if I put 2 in the bottom, I'll get 0. So I get 0 over 0. And when we got 0 over 0 before, what we did was we factored the top and factored the bottom and then canceled what we could, and then usually we could find the limit from there. But what if we happen to have the limit as x goes to 2 of the natural log of x minus 1 over 3x squared minus 2x minus 8? Again, if I put 2 in here, I'll get the natural log of 1, which is 0. And if I put 2 in the bottom, I'll also get 0. So again, I get 0 over 0. It's called an indeterminate form, but I can't factor this to solve it. So we need to figure out how do we find these limits when we can't actually factor. So we'll go on and look at the process behind this. So first off, we have what we call indeterminate forms. In other words, we can't find the limit of those because we don't know what they are. They are 0 over 0 and also infinity over infinity. 0 over 0 is not 0. It's not 1. We don't know what it could be. It could be 5 for all we know. Same with infinity over infinity. Infinity over infinity is not 1. It's not infinity. It could be 0 for all we know. And so the process is we want to actually talk about how we find this. And so 0 over 0, these are called indeterminate forms because we can't figure out what they are from just taking the limit. We have to do some more work to them. So 0 over 0 means the limit as x goes to some number, let's call it a, of f of x over g of x equals 0 over 0. That means that as f of x goes to 0 and g of x goes to 0 as x goes to a. Infinity over infinity means that the limit as x goes to infinity of f of x over g of x equals infinity over infinity, which means that f of x goes to infinity and g of x goes to infinity as x goes to infinity. And so we have to figure out what to do with these. And this is where L'Hopital's rule comes into play. L'Hopital's rule says, suppose you have f and g are both differentiable and g prime of x does not equal 0 near a, except possibly at a. So then suppose that the limit as x goes to a of f of x equals 0. And the limit of as x goes to a of g of x also equals 0. Or they both equal infinity. Then the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. This isn't the quotient rule. We're not doing the quotient rule here. We're just taking the derivative of the numerator and the derivative of the denominator to do this limit. Again, this is not the quotient rule. This does not replace the quotient rule. It's just a rule we use to find these limits. So let's go look at how to do one of these. Let's take an example. Let's say we want to find the limit as x goes to 2 of x squared minus 4 over 3x squared minus 2x minus 8. Again, we can solve this by factoring, but we can do it a different way. Let's show you the different way we can do it. So first thing to check is, does it in fact get you 0 over 0? Is it an indeterminate form? So you put 0 on the top. If you put 2 on the top, you get 2 squared minus 4, which is 0. If you put 2 in the bottom, you get 3 times 2 squared minus 2 times 2 minus 8, which also happens to be 0. So we do in fact get 0 over 0, so we get one of the indeterminate forms. That means we can use L'Hopital's rule. So the way that I do L'Hopital's rule is what I like to do is just think of it as I'm going to L'Hopital the top and bottom. So I like to put a little H here with a circle around it that just tells me I did L'Hopital's rule. You don't have to. It's just a good reminder. So when you look back, you know what you did. So we have the limit as x goes to 2. L'Hopital's rule says if you get the indeterminate form, and both of these are differentiable functions, which they are, and the limit of the bottom, the derivative does not equal 0, except possibly near 2. So what we're going to do now is we're going to look at what is the derivative of the top and the derivative of the bottom. So the derivative of the top is just 2x. The derivative of the bottom is 6x minus 2. So we have, now we're going to take the limit of this. So we're going to find the limit as x goes to 2 of 2x. Put the 2 in, you get 4 in the top. Put 2 in the bottom, you get 6 times 2, which is 12, minus 2 is 10. So we get 4 over 10 or 2 over 5. And that happens to be our limit. And so notice it's not 1, it's not 0, it's 2/5. If you looked at the graph of this, you would see it was heading towards 2/5. Okay. Let's try another one. Let's find the limit as x goes to 2 of the natural log of x minus 1 over 3x squared minus 2x minus 8. Again, this was the one we saw in the when we first started, but we're going to check it anyway. So you always check it to make sure you get indeterminate form, because if you don't, you can't use L'Hopital's rule. So put 2 in here, you get the natural log of 2 minus 1, natural log of 1 is 0. Make sure the bottom is 0 too. Put 2 in here, you get 2 squared, 3 times 2 squared minus 2 times 2 minus 8, that also will be 0. So again, we get one of the indeterminate forms, so we can use L'Hopital's rule. So again, I like to put this little h here just to remind me when I go back to look to what I did. You don't have to. It's just a reminder for me to know what I did. And so it could be a reminder for you. Now, L'Hopital's rule says take the derivative of the top. The derivative of the natural log of x minus 1 is 1 over x minus 1 times the derivative of the inside. The derivative of the inside is 1. Then the derivative of the bottom will be 6x minus 2. So we're going to put 2 in. We're now going to take that limit. So you put 2 in for x. You get 1 over 2 minus 1, which is 1. So 1 times 1 is 1. In the bottom, you're going to get 6 times 2 minus 2. 6 times 2 is 12, minus 2 is 10. So you get 1/10 as this limit. Again, it's not 0, it's not 1, it's 1/10. And again, if you looked at the graph, you would notice it looks like it's heading towards 1/10. Let's try some more. Let's find the limit as x goes to 0 of x plus tangent of x over sine of x. Again, put the limit, try the limit. You want to see what you do when you try to do this limit. Usually when we do limits, we can put 0 in for the x. Because these are continuous functions, we can do that. So you're going to put 0 in the top. 0 plus the tangent of 0 is 0. And the bottom, the sine of 0 is 0. So again, this is one of those indeterminate forms. So we can't actually do what we just did because we get an indeterminate form, but we can use L'Hopital's rule because we got an indeterminate form. And L'Hopital's rule says take the derivative of the top and derivative of the bottom, and then take the limit of that. The limit of the top will be 1, because we had x plus tangent x, it's 1 plus the secant squared of x over the derivative of sine is cosine. Now that we've done that, let's take the limit. So now put 0 in, get 1 plus secant squared of 0. Secant squared is 1, and 1 squared is 1. So you get 1 plus 1. The cosine of 1 is 1. So you get 2 over 1. So you get 2. So we now know that that limit is 2. Again, it's not 0, it's not 1, it's the number 2. Let's try this one. This is the limit as x goes to infinity of e to the x over x cubed. So again, let's try finding out what that limit is. If we put infinity in for e to the x, e to the infinity is infinity. Infinity cubed is infinity. So we get infinity over infinity. Again, this is one of the indeterminate forms, so we're good. So we can use L'Hopital's rule. Always check that, because if it's not, you can't use L'Hopital's rule. So let's take the limit as x goes to infinity now. Let's take the derivative of the numerator. Derivative of the numerator is e to the x. The derivative of the denominator is 3x squared. Again, try this again. Put the infinity in, you're going to get infinity in the top, because e to the infinity is infinity. And 3 times infinity squared is still infinity. Ooh, so we get the indeterminate form again. So that makes you wonder what you can do. But again, these are all functions. So we still have the same process of L'Hopital's rule. We still have a function that's continuous over a continuous function, and both differentiable functions, I should say, because that's more important, is they're both differentiable, and we still get infinity over infinity. So we still get an indeterminate form, so we just do L'Hopital's rule again. So that'd be the limit as x goes to infinity of e to the x, because the derivative of e to the x is e to the x. The derivative of 3x squared is 6x. Again, now try finding out what the limit as x goes to infinity of e to the x is. That's infinity, because you really can't do e to the infinity, but e to the x goes to infinity as x goes to infinity. 6 times x also goes to infinity as x goes to infinity. Again, we get that indeterminate form, so we're just going to keep doing L'Hopital's rule so you no longer get that indeterminate form. So we have e to the infinity, as e goes to infinity. I'm sorry, first we have to do the derivative. The derivative of e to the x is e to the x. The derivative of 6x is 6. Now, as x goes to infinity, e to the x goes to infinity. As x goes to infinity, 6 goes to 6. So we no longer get an indeterminate form. We get infinity divided by 6, which happens to be infinity. So in this case, infinity over infinity is infinity. It's not always. It just happened to be in this case. And so sometimes you do L'Hopital's rule several times to get the answer. Let's try another one. Let's look at the limit as x goes to pi of tangent of x over x. So as x goes to pi, the tangent of x will go to 0. And as x goes to pi, x goes to pi. So we get 0 over pi, which is 0, and there's nothing to do with L'Hopital's rule in this case because it wasn't an indeterminate form. So make sure you get an indeterminate form. If you don't, then just find the limit. So we can do this limit without L'Hopital's rule. And we only use L'Hopital's rule because we get something we can't do. Let's try another one. Let's actually look at another type of form. So we have other indeterminate forms. This one is of the type 0 times infinity. So when we have that, we have a limit as x goes to some number a of f of x times g of x. Either f of x goes to 0 and g of x goes to infinity as x goes to a, or the other way around. Doesn't matter which one goes to where, but one of them goes to 0 and one goes to infinity as x goes to a. To do this, we actually need to use L'Hopital's rule, and L'Hopital's rule needs 0 over 0 or infinity over infinity. So L'Hopital's rule needs to have a fraction. So we're going to use the fact that we can actually change f of x times g of x into f of x times 1 over g of x. Or 1 over f of x times g of x. Either way, you're going to make this into a fraction. And just by making one of these into a fraction. So let's try an example of this. Let's find the limit as x goes to negative infinity. You can go to infinity or negative infinity. It doesn't matter which one. Of x squared times e to the x. As we're going to negative infinity, x squared will go to negative infinity. As we go to negative infinity, e to the x, if you remember what e to the x looks like, e to the x looks like this. As x goes to negative infinity, we're going to go to 0. So we end up getting negative infinity times 0. So all we have to do now to do L'Hopital's rule is we have to first change this into a fractional statement. And it really doesn't matter necessarily which one you do, but it's just going to make it easier for you to do one over the other. So sometimes I try one, and if that doesn't work, I try the other one. What I'm going to do is I'm going to try actually making e to the x into a fraction. If I do 1 over e to the negative x, that now is a fraction. 1 over e to the negative x is e to the x. So I haven't changed anything at all. I've just made it into a fraction. Now let's try the limit. The limit as x goes to negative infinity of x squared is still negative, well, actually it's positive for infinity. I apologize. That should not have been negative infinity. X squared is always positive number, so it goes to positive infinity. 1 over e to the negative x. As x goes to negative infinity, e to the negative x. So let's look at e to the negative x. E to the negative x looks like this. So sweeping down, going towards infinity goes to 0. As we go towards negative infinity, it's going to go towards infinity. But 1 over infinity is 0, but we have 1 over infinity. So we get infinity over infinity, which is what we wanted. We get one of L'Hopital's rules. And we can see it worked out. It was still what we had originally because we still have infinity times 0, but we now have infinity over infinity. So we can now use L'Hopital's rule. And L'Hopital's rule says, take the derivative of the top and the derivative of the bottom. So our top is x squared, so the derivative of that is 2x. Our denominator is e to the negative x, so that's negative e to the negative x, because the derivative of the outside is e to a power, and then times the derivative of the power. And the derivative of negative x is negative 1. Now, try again, find the limit. As x goes to negative infinity, 2x actually goes to negative infinity. As x goes to negative infinity, e to the negative x goes to infinity, so we also get negative infinity. So we get negative infinity over negative infinity, which is infinity over infinity. And so we again get indeterminate form. We can again do L'Hopital's rule. L'Hopital's rule says that limit as x goes to negative infinity, that will be 2. The derivative of the top is 2x is 2. The derivative of the bottom is e to the negative x. Because again, you take the derivative of the outside, which is e to the power, then times the derivative of the power. The derivative of negative x is negative 1, but we had a negative sign. Now go ahead, take the limit as x goes to negative infinity. Well, 2 goes to 2. And as x goes to negative infinity, e to the negative x is going to go to infinity. So we get 2 over infinity. 2 over infinity means actually 0, because as x gets really, really, really big, 2 over that is going to get really, really, really small. So we do, in fact, get 0. And again, it's just coincidence that 0 times infinity is 0. 0 times infinity could be infinity. It could be 5. It could be, in this case, 0. Another indeterminate form is infinity minus infinity. So this happens whenever you have the limit as x goes to infinity, or as x goes to anything, actually, x goes to any a, of f of x minus g of x, where f of x goes to infinity and g of x goes to infinity as x goes to a. To do this, you're going to convert this difference into a quotient. And so it depends on the problem of what you're going to do. Usually it means that we're going to multiply numerator and denominator by the conjugate of that numerator to change it into a quotient. We'll see how that works. So let's take the limit as x goes to 0 of cosecant x minus cotangent x. So the limit of that as x goes to 0, as x goes to 0, cosecant is 1 over sine, and 1 over sine goes to 0 as x goes to 0. So 1 over cosecant goes to infinity. Cotangent is 1 over tangent, and as x goes to 0, 1 over tangent goes to 0. So 1 over that will go to infinity. So we do, in fact, get infinity times infinity, or infinity minus infinity. So before we can use L'Hopital's rule, we need to get it into infinity over infinity or 0 over 0, either one of those two indeterminate forms, because L'Hopital's rule only works if you have 0 over 0 or infinity over infinity. So let's see what we can do with this. Well, I just said cosecant was 1 over sine. This time we're not using conjugate because we're going to use the properties of sines and cosines, or trig functions. Cotangent is cosine over sine. And now what I notice is I actually happen to have the limit as x goes to 0 of 1 over sine minus cosine over sine. I actually can combine those two fractions together into one fraction. That will give me 1 minus cosine. Over top of sine. Now let's see what that is. So as x goes to 0, 1 minus cosine will go to 1, and 1 minus 1 will go to 0. As x goes to 0, sine of 0 is 0. So we get 0 over 0. So we finally changed this over from infinity minus infinity into something that we can work with using L'Hopital's rule. So now let's use L'Hopital's rule. L'Hopital's rule says take the derivative of the top. The derivative of 1 is 0. The derivative of minus cosine is sine. Then take the derivative of the bottom. The derivative of the bottom is cosine. Now try to find this limit. As x goes to 0, sine goes to 0. As x goes to 0, cosine goes to 1. So we do, in fact, get 0 over 1, which is 0. So in this case, infinity minus infinity is 0. But again, infinity minus infinity could be 0. It could be 5. It could be infinity. It could be lots of different things. One last one I want to look at is what we call indeterminate powers. This is the limit as x goes to a of f of x to the g of x. One is that the limit as x goes to a of f of x equals 0, and the limit as x goes to a of g of x equals 0. This is a type 0 to the 0. You've always been told that any number goes to 0 except 0 itself. I'm sorry, any number to the 0 goes to 1 except 0 itself. This is where we're going to finally find out what 0 to the 0 is. And unfortunately, it's one of those indeterminate forms. We don't know what it is. It's not 1. It's not 0. It could be, but it's not necessarily those. It could be 17. We don't know. The limit as x goes to a of f of x equals infinity, and the limit as x goes to a of g of x equals 0. This is a type of infinity to the 0. So we've always told you that any number to the 0 is 1 except for 0, but also except infinity. Infinity to the 0 is not also 1 either. And the last one is the limit as x goes to a of f of x is 1, and the limit as x goes to a of g of x is infinity, so you get the type 1 to the infinity. 1 to any number is 1 except infinity itself. We don't know what 1 to the infinity is. Again, it could be any number. So let's try one more of these. Let's find the limit as x goes to 0 from the right of sine of x to the tangent of x. Now we're only coming from the right because tangent does some interesting things. So we're only going to look at it from that point of view, but there's no big deal with that. Okay. So what we need to do is we need to figure out what that is and how to go about doing this problem. So let's see. First thing you're going to do is find out if you do in fact have the right form. So the first thing we're going to do is find out what the limit is. As x goes to 0, you get the sine of 0 is 0. The tangent of 0 is 0. So you do get 0 to the 0. Again, we don't know what that is. We don't know what the value is, and we're going to try to find out what it is. So the process we're going to do for these, because you've got a power, usually when we have a power, we're going to go ahead and let y equal that sine of x to the tangent of x. And the reason we do that is because when we have a power, we know that we can take, if we take the natural log, we can bring that power down in front. And so we want to be able to do that, but we need an equation to do that. So that's why we made y equals sine of the tangent of x, so we can take and do the limit. I'm sorry, not the limit, the natural log of both sides. Because without an equation, I can't just take the natural log. So I needed to have an equation. So I got an equation, y equals sine of tangent of x. Take the natural log of both sides. Natural log of y is the natural log of sine of tangent of x. Bring that tangent down. That's tangent of x times the natural log of sine. So that's now what we have. We're going to, again, what we're going to do is we're going to find the limit as x goes to 0 from the right of the natural log of y. And then the limit as x goes to 0 from the right of the tangent of x times the natural log of the sine of x. Okay. So let's see what we can do with this. So we're going to worry about what this limit is over this side in a moment, but let's go ahead and do this other side and see what we can do. If I try to use try to do the limit, I get the tangent is 0. So as x goes to 0, the tangent goes to 0. As x goes to 0, the natural log of the sine of 0. Well, the sine of 0 from the right is 0. And as we're coming from the right towards 0, the natural log is going to go to infinity. So we get 0 times infinity. So we have to do a little bit of work here. This is kind of L'Hopital's rule. It looks like it's going to be, it's one of our indeterminate forms, but we need to get a fraction. It would not be easy to make the natural log of sine of x into a fraction, but it's really easy to make the tangent. Tangent is 1 over cotangent. So we now have the limit as x goes to 0 from the right of 1 over cotangent times the natural log of sine of x. Well, 1 over cotangent of x as x goes to infinity goes to infinity. And we already determined that the natural log of sine of x goes to infinity. It actually goes to negative infinity, but it's still the same idea. Okay, so now I have infinity over infinity. Even though it's negative infinity, it still works. I can now find L'Hopital's rule. So L'Hopital's rule says take the derivative of the top. The derivative of natural log is 1 over whatever. So 1 over sine x times the derivative of the inside. So the derivative of sine x is cosine x. The derivative of the bottom, the derivative of cotangent is cosecant squared of x. So let's see if we can't simplify this just a little bit to make it look a little bit nicer. So we now have the limit as x goes to 0 of cosine over sine, which is cotangent of x, over cosecant squared of x. Okay. Well, let's see if we can do with that. Let's see if we can do anything with that and see what we get. So again, as x goes to 0, the cotangent will go to infinity. The cosecant squared will also go to infinity. So again, we get infinity over infinity. So that tells me use L'Hopital's rule again. So we have the limit as x goes to 0 of the cotangent, which is the derivative of cotangent is cosecant squared. Derivative of cosecant is 2 of cosecant squared is 2 times cosecant times the derivative of cosecant, which is cosecant times cotangent. And then simplify this a little bit. You have cosecant squared and you have another cosecant squared, so we actually get 1 over 2 cotangent x, which is 1 over 2. Let's actually make this into cotangent is cosine over sine, so we get sine over cosine. And the limit, oh, forgot my limit. Limit as x goes to 0 of sine is 0. Limit of cosine is 1, so we get 2, so we get 0. Now we're not exactly done. That's actually what the limit as x goes to 0 of y is, of the natural log of y. And that equals 0. So now we have to figure out what to do with that. And that would be the limit as x goes to 0 of the e to the natural log of y, because this was just the natural log of y. And then you'll get oops. All right. So actually, I don't think I'm going to do that. We want to find out what this limit is and see what this is equal to. And oh, so we can actually go back to the fact that our y was the limit as x goes to 0 of e to the natural log of y. And e to the natural log of y is y, so that works out. And the limit of e to the y of this natural log, so remember you can do e to the limit of the natural log of y, but we now know the natural log of y is 0, so we get e to the 0, which is 1. And there's L'Hopital's rule.